Welcome back, friends. In this video, we are going to find the zero of a function using Newton's method in C++. As usual, the algorithm first and then the code. So let's simplify. Newton's method is one way of finding the location of the zero or the root of a mathematical function, f of x. The method works by initially guessing the x location to zero. The functional value at the current x is computed to get a better estimate of the zero. This process is repeated until the difference between two successive estimates is at most 1 in 10 million. Each estimate of x new is computed from x old as follows, where f prime of x old is the derivative of the function f of x old. Given that f of x equals 5x squared plus 4x minus 72, write a computer solution that will accept as input an initial guess value x old and then find the zero of the above function. Your output should be the zero of the function and the number of iterations performed to obtain the root. The algorithm. We are going to ask the user to input an initial guess value x old. So we say input x old. Now we're going to store a copy of this x old in a new variable called x new. As we go along, I'll explain further. Now we're going to create an empty variable called counter, which is going to store the number of iterations that will be performed to obtain the root. Now, since we are supposed to repeat the process, we are going to use a do while loop. So we say do x old equals x new. Then we print the formula x new equals x old minus f of x old divided by the derivative of the x old, then counter plus plus. Now, in this loop, what is going to happen is that the values for x old and x new is going to change. So as they keep changing, what we want to do is that we want the first x old value to be the value that the user entered in this loop. So what we are going to do is that, remember we stored a copy of the user's x old in x new. Now you see in this while loop, do while loop, we have given that x new back to the x old. Now we put that x old now into the formula so that it will be the first value. Then we compute for x new. Then when you compute for x new, we increase counter by 1. Then we give that x new back to the x old. And we put that x old into the formula, find x new, increase counter by 1. Put the x new back to the x old. Put the x old into the formula, find for x new, increase counter by 1. Then give the x old back to the x old. Give the x old into the formula. Then find x new, increase counter by 1, put the x new, give the x new to the x old, put the x old into the formula, find x new, increase counter by 1. So it keeps going on. You give the x new to the x old and you put the x old into the formula and you find the x new. So this loop keeps going on. Now as this loop keeps going on, we also be increasing counter by 1. Then we'll also be checking if the difference between the x new and the x old, because from the question said the successive estimates, the difference between them. So if the difference between the x new and x old is approaching 1 in 10 million, then we should end this while loop. So the moment it approaches 1 in 10 million, we end this loop and then we print our results that the zero of the function is the value of x new. And the number of iterations performed, or the number of repetitions, is the counter. You remember we always increase counter by 1. Now you see here that this f of x old and f of the f derivative of x old, these are functions that have already been defined and has been called in here. So what we are going to do is that we are going to actually define them somewhere. So we declare them somewhere here. So we say functions. Then the function we are supposed to find the x old of, we write it there. So f of x equals 5x squared plus 4x minus 72. And then we find the derivative of that, which is 10x plus 4. Now the x old that the user inputted, you can see that that x old in the f of x old, that x old is going to be the x value in f of x. We are going to compute for it. Then that same x old is going to be the x in the f dev from this function here, which will also be computed over here. So we actually can't find this without these functions. So we must first define these functions before we come here so that we know what f of x old is and what f prime of x old is. Alright friends, so let's see how this whole algorithm will look like in C++. So before, now you can see I included the CMAX library because I'll be using the power function. Then before the int main function, I declared the question we are supposed to compute for. So I said inline double f double x, where we'll be putting the x old, return f times x to the power 2 plus 4 times x minus 72. Then again, I do that for the derivative of f derivative will be 10 times x to the power 1 plus 4. So because I've already defined these functions, I can declare them, I can call them inside the int main function. So I set counter to be an integer and then x new and x old to be doubles, because I'll be taking x old as a double in the function here. So you can see double x here. Then I take the initial guess from the user, and as usual, I interchange them here. And in the do while loop, I compute for the x new. And you know that this f and f dev here have already been defined. So whatever x old is going to be, you're going to put that where the double x is. And where the double x is here will be the value of x inside this function and also the f dev function over here. Then we compute for it until the difference between them approaches 1 in 10 million. Then when it approaches, we print out that cout that x new is the value for the root, and then the number of iterations will be counted. Then I end my code with system pause. Now let's try some values and see how our code runs. So for the function we were given, which was f of x to the power 2 plus 4x minus 72, I'm just guessing that the x value or the root of that function will be 2. So when I press enter via my keyboard, it says that actually the x root, the root of that function is 3.41576, and the number of iterations performed was 5. So you can see that even though my guess was wrong, the Newton's method was still able to compute for the actual answer. Then the number of iterations, because of my guess, was 5. So your number of guesses will also sometimes determine the number of iterations to arrive at the answer. Alright friends, that's it for this video. See you in the next problem. Don't forget to like and subscribe. Till then, apart, yeah.